So we're going to get started. So basically, what this is this is part one in a two-part on lithium in batteries. And so we're going to cover in this one kind of the basic sort of what, how, when, where, why it's used, and kind of primer for the next one, which is going to be lithium mining, refining, and recycling. That was the real goal of what we were trying to put together. And we realized about halfway through making that presentation that we couldn't do that one efficiently in one go and had to kind of do a primer first on sort of what it is and how it's used and why it's important. And then we could do the one we actually want to do, which is the nitty gritty, how it's mined, the different types, the different versions, the different processes, how it's then refined, how those are used, how that impacts everything. And then can it be recycled? And if so, how and why, and what the costs and problems are.
Yeah,
so,
our draft, I think, was like 130 slides to start. So like, we didn't want to put you guys through that.
Yeah. So just real quick, our goal is to basically talk about interesting things in the battery industry and talk about things that in some cases, Jeff and I can run into that we work with on a daily basis that are not overly shared. And so we like to just kind of bring things up that people are interested in and talking about and want a little bit more information about, or maybe some sort of qualified opinions about, and that's how we chose these topics. Everything we show, we try to keep it public because Jeff and I both have about 1 billion NDAs that we have signed. Me especially, because I work in a consulting company. So everything here is public, and we put these up online on YouTube, and this will all be available if people have to drop out early or want to see it again later. So real quick, just me, my name is Aubert. I work at Spectra Power. Again, like I said, we do R&D consulting and prototyping and energy storage. I'll keep that really short. And Jeff, if you want to say a couple words about yourself.
Yeah, sure. I'm Jeff Bell. I work at Lighten. We do lithium sulfur batteries. I run the data analysis, cell design, and integration teams there.
Cool. All right, let's get started. So lithium. What is lithium, and why do we all care about it, right? So basically, lithium does not really exist on its own. You have to extract it from the many ways it's actually found in nature to get it to the nice shiny lithium that we typically use in lithium metal batteries, or the different components that go into making basically the cathodes for lithium ion or the salts for the electrolyte, right? So the lithium hydroxide, the lithium carbonate, the LiPF6.
Yeah, and usually it's found in nature in the form of either a spodumene, a petalite, an ambient or lepidite, and then that goes into what our next presentation will concentrate on, the refining. But overall, what we can say is lithium is a highly reactive alkaline metal that is very desirable, as we'll get into later. So
lithium being used in batteries has basically taken off in the last 10 years and the last couple of years especially. So if you go back to, like 1990s, it's a very tiny percent of the market. But even as recently as, 2011, it was about 1/3. And now it's about 3/4. And that goes up every single month as we head towards, EVs. And if it ever actually mistakenly gets used for grid storage and scale, that percent's going to be like 99%. All right, Jeff, take it away.
All right, so why is lithium important? Basically, guys, the reason lithium is important is 1, its standard production potential, and 2, it's ultra light. So it's basically the third lightest element relative to hydrogen and helium, and it's also really, really small, which means it can get into really, really small things as well in tight passageways. And that's critical when you're doing the science for batteries. So if you flip to the next slide, Aubert, really the takeoff.
One thing briefly before we get to that, but for you non-technical people, right? It's very tiny and it's very light. And we'll talk about that more later, but its position on the periodic table is really critical. And also, if everyone here has been paying attention to battery news recently, you've seen that a lot of people have announced they're going into sodium-ion batteries. And if you'll look over here at the periodic table, which for the non-chemists in the room, you probably don't do very often, you'll notice it's adjacent. And there's really good reasons for that because it's all the same properties. And people have looked at doing potassium-ion batteries as well, which doesn't really work. But there's very good reasons for that. And we'll cover those in the next slide, which is what Jeff wants to get to.
Yeah, so why lithium ion? Basically, why we're using it is mainly because of its performance characteristics, guys. So basically, if you compare it to like nickel metal hydride, nickel cadmium, lead acid, lithium ion, and all those, you'll see that lithium ion in general, or lithium polymer, or the lithium metal batteries, all significantly exceeded from a watt hours per liter and watt hours per kg point of view. But that's not the only thing really, right? So why else? Well, one, beyond just having the highest commercial energy densities, it's able to deliver a large amount of current to high power applications. And that's usually due to its nominal voltage. If you look at a lot of the other lower voltage chemistries, they actually get penalized. So they can deliver, like, let's say, an amp of current, but that really only equates to maybe 2 watt hours, where with the 3.6 volt nominal voltage window, you get a huge advantage in terms of being able to get that energy out of the system as a result. So the same 1 amp of current that you would get out of a lithium ion battery related to maybe a lead acid would give you 3.6 watt hours versus maybe 1 to 2. Another thing is this memory effect. So I don't know if you guys remember the nickel metal hydride and the nickel cadmium days, but older or other chemistry technologies tend to have what's called a memory effect. So essentially when you would do partial depths of discharges, another way to say you only use maybe 30% of the capacity window, the cell would actually start to remember that over time. And when you tried to go back to a full depth of discharge, it would actually, that memory effect would negatively impact that, and you would artificially lose capacity of the cell, even though you were only doing partial discharges. Another huge one, and this is actually why you see it in a lot of long-term applications, or why your cell phone is able to work and hold its charge so well, is really the low self-discharge. Lithium metal batteries, or lithium ion batteries, are basically 1.5 to 2% a month, which is incredibly low. We already covered the high charge to weight ratio, but around that low self-discharge, right? That's really being functioned by, it's really unlikely for lithium metal to be replaced by substitution within a chemistry. It's essentially third lowest on the standard reduction standard reduction potential table. So that puts it at basically, there's not much. Lithium will react with most things. Not most things are going to displace lithium from what it's already inside.
And again, really quickly, again, for the non-chemists, small and lightweight for the lithium ions are one of the driving factors, again, just to push this again on how it gets such good watt hours per kg and watt hours per liter energy density metrics, which are the things you hear all about on what matter from a performance perspective.
Yeah, that's that charge to weight ratio, basically, where it is on the periodic table, is how much charge is lithium giving you per weight of it. And that's why we say it's so light and everything is good.
Okay, so first part of why we care is because basically it's now being used in EV batteries. There's other potential uses, but in terms of the, again, watt hours per kg and watt hours per liter, requirements to make that happen from everything from electric bikes to electric scooters, EV buses, and electric vehicles, in order to get the basically equivalent efficiency and the range that people want at the cost. They're not going to get the cost at this point, but at the cost goals, there's really no other chemistries that really work right now that are commercial. And so what that means is we have to use lithium in order to make EVs currently. Was NMC, it's going towards LFP. We'll talk sodium ion in the future, but that's not going to happen in the next couple of years. And basically, on a car, and here's an example one with a 60 kilowatt hour battery pack, you're using about 9 kilograms of lithium, which is an enormous amount. And that's really kind of the focus of today, is the amount of lithium being used for EVs in lithium ion and other chemistries, and then why and how that impacts everything else.
So
go ahead.
I was going to say, so like, kind of related to the EV story, I think we've all heard the news, and this is like one of the big drivers. Everybody is opening a gigafactory, right? So lithium, a conversation about Lithium 101 is kind of apt, and it's going to be even more apt in the following slides. And that's really around how many people are trying to establish a footprint in the US for manufacturing. And I think it's no news to everyone else here that the IRA has come out. The first tranche of a couple $1 billion went to companies doing what we would call state of the art. So, you know, do they produce copper? Do they produce aluminum foil? Do they produce graphite? Do they produce any of the cathode materials, NMC, NCA, LMO, LFP, etc.? What electrolyte? Do they produce a standard carbonate-based electrolyte? And then do they produce silicon? in some quantity, because even today batteries have 4 to 7% or 4 to 9%, depending on whether it's pure silicon or a silicon monoxide inside of the battery itself.
Okay. So, and again, on the sort of first order of why this matters right now, why people care. And the answer is because of the enormous price spiking we've seen in the last couple of years. And so both for the components that are used in actually making the cathodes, which again are the most expensive and in many cases the most critical component in a lithium ion cell, the lithium hydroxide, the lithium carbonate, those prices have gone just absolutely insane in the last couple of years. They did come down a little bit this year. There's a lot of reasons for that. I fully expect that it did this and that it's about to keep going back up. We'll see if we're wrong or not. There's a lot of hotly contested information about that we'll present shortly. But basically, the lithium prices have gone incredibly high. The lithium hydroxide prices have gone up a lot. The lithium carbonate prices have gone up, and the lithium metal and the ingot prices have also gone way up. And those are some really big factors in the direct raw material costs in lithium ion and lithium metal batteries.
Yeah, so before we continue, Tom, it looks like you raised your hand.
Just
Yes.
how much of the market gets done at these prices? I thought that there were long-term supply contracts.
So
Most of it.
there is long-term supply contracts in place. There's also a lot of assumptions in place in those long-term supply contracts, as we'll get into later. But you also have the issue that a lot of those early long-term supply contracts were based at quantities, which are, it's really hard to predict how hard something is going to rocket or spiral off. So maybe the pricing in that was advantageous to the early procurer of that long-term contract, but the quantities may not scale with that price.
Yeah,
So,
and we'll go into this more later because this is a really big crux of what we're talking about. But basically, every gigafactory that's announced is going to increase the cost. Every mine that's successfully opened and refining station that's successfully opened and goes online will increase the supply and reduce the cost. And right now, the first one of those is happening a lot faster than the second one of those. And basically, because people are sort of, there's a fear about material scarcity, and like to the point where literally OEMs are buying the materials 3 to 5 years out for whatever cell maker they're going to use to be able to make them electric vehicle batteries. That's like revolutionary. Like that doesn't happen in other industries, right? You don't see that kind of thing happening in pretty much anything else. And the things people are scared about right now, really, lithium is at the very top of the list, because if you don't have lithium, you don't get a battery. You don't get a battery, you don't make EVs. And it's really that simple. And if you have been around for a while, you probably have okay supply agreements, but even companies like Tesla are basically looking at how do we set up our own lithium mining and refining? How do we control a supply chain going forward? Otherwise, they'll be restricted in how many cars they can make and sell.
yeah, I mean, that's
what they're scared
echoed.
of.
That's echoed by, Tesla getting into LFP, everybody starting to vertically integrate to some extent, to just trying to avoid the cost inflation they're going to have to deal with. Because the real fear is, as production picks up from the big pandemic we came out, the concern is, will demand again outstrip the supply at the current rate?
Really quickly, I saw a question on recycling. So this is part 1, and part 2 is going to be mining, refining, recycling, and that will be next month. So we will talk a lot more about that later. But the short-term answer is right now, not very well. To the question in chat on can lithium ion batteries be recycled? And the answer is not well, not efficiently, not at cost, and you don't get most of the components back. And lithium is one of those things you don't tend to get back. So really quickly, for those of you that do battery R&D, you're familiar with prices like this, which are basically paying an arm and a leg for components in small quantities. The pro tip, as you said, buy in larger quantities, get your supply agreements in place. Even if you're a small company, you can definitely get kilograms of stuff, and you'll be paying the same for that as you will for the grams you're buying now. It'll be better quality, it'll be newer, you'll have the history of the shipping, and then you can do more things with your experiments for the same money. There is an enormous amount of disparity on purity grade refining and pricing, and you'll see the difference between 99.5, 99.9, and 3.9s and stuff be orders of magnitude each time you do that. And that's actually one of the big problems for lithium, is because the purity really, really, really matters, but it also really, really, really drives price.
You also have to be careful. Purity in lithium metal is actually driven by a base set purity profile. So it doesn't, like, when someone says something is 99.999% pure, it's not 99.999% pure against the entire periodic table. It's 99.999% pure around a few select elements the supplier believes are critical for what makes lithium metal, and that's usually in a drawing somewhere.
Mhm. And real quickly, just to answer the comment from James Dean, 100%, there's ways to do it, but I don't think economically. It's going to take a lot of subsidies and a lot of penalties, I think, before that's actually going to be done. And it kind of brings up the problem where things like LFP batteries, there's not much worth recycling in an LFP battery to begin with. So
Yeah.
you're basically getting the copper, and maybe you go for the lithium. That's not very incentivizing. We're going to talk about that next time.
Yeah, we'll talk this next time. The best way to think about it is if you sell an 18650 or a 21700 for $8, and that includes a margin, that means after you have recycled all those things, your entire production process means you have to resell that battery for $8. So think about that just for a second. If you're selling batteries for $8, all your recycling processes have to be cheaper to make that battery again at $8.
Drastically cheaper than a small fraction of that $8 if you want to plug them back into these materials.
If you want a zero margin business.
So anyway, there's about 1 billion caveats on this pricing. It is very, very, very hard to find actual long-term industry stable pricing, like you said earlier. I believe it was Tom. And one of the things you can do is you can just look at the spot pricing, and you can look at kind of what you can buy medium quantities for online, and you kind of look at a point in the middle and apply some logic to it. But these are kind of the raw pricing right now of what you can find for the quantities in ton scale, for these materials in ton scale. So we just took those, reduced them down to kilograms. Nothing here accounts for the shipping, the handling, the insurance, the processing, except for the ingots to foil, which you have to do, or different purity grades and costs and requirements. And kind of one of the bigger takeaways you'll see soon is that if you're not vertically integrating your lithium metal production, you are probably in a lot of trouble.
Mm-hmm.
So
here's this lithium equivalent content. So this is the best way to put this is, as lithium prices went up, there was this discussion in the industry, probably run by marketing, is what is the most lithium efficient chemistry, aka what chemistry gives you the best amp hours or watt hours for its buck. And Aubert and I wanted to tackle that question because most of us would think, right, to get an amp hour of lithium or an amp hour of energy or capacity, I mean, you would need to move one lithium to make that occur. So we did all the math. So I'll give you some assumptions. So all of these batteries you see in the right chart and on the left chart are actually, I designed them myself. I held all the electrolyte data, amp hour ratios constant for everything but solid state, which doesn't supposedly have it. Although we know most of them do. 2, lithium sulfur, it's just a different animal. And that's something I specialize in. So I'm aware that there are changes there. And then 2, we kept all the cathode loading. So we basically sweeped a bunch of cathode loading, said 3, 6, 9, 12, and 15 milligrams per centimeter squared of loading for each of these chemistries. And then what we said is we wouldn't do lithium metal free anodes. 1, they don't really work, but 2, it would be basically NMC 811 because you'd be replacing the graphite with just a bare thing of copper. So you would just have roughly the same amount of lithium in the system anyways, because your amp hours to electrolyte would stay constant. And then packaging and foils are all the same. So there's no variation in terms of, like, I chose this to have in Mylar, this was a cylindrical cell. They're all pouch cells. They're all at the same stack configuration. They're all at the same tab width and everything else. What you're going to immediately draw your eyes to is that LFP kind of crushes everything, right? And from both amp hour per gram of lithium and watt hour per gram of lithium. But the unfortunate truth of this is it isn't really the entire story, because if you look at it from a per unit energy assigned, it wins, but that doesn't really equate to either cost or performance, right? So if you flip to the next side, what you'll see is that if we look at it from the point of cost per amp hour and cost per watt hour, suddenly lithium sulfur is beating it, right? It suddenly flips most of the axes. Solid state still sucks. So does liquid lithium metal, but everything kind of flips, right? NMC 811 is getting closer, NCA is down there, LFP suddenly isn't a huge stretch of the margin away from an NCA battery or an NMC 811. I didn't do 9.5, but that'll be even closer in that graph, and lithium sulfurs a lot closer. So when you look at cost per kilowatt hour, per amp hour, suddenly the units of everything changes, right? So if you're looking at it for like how much energy or how much capacity I get out efficiently for using lithium metal as a chemistry, it's one story. If you look at it from a cost point of view, it's a different story. So really it's like, do we want to be lithium efficient or do we want to be cost effective, right? And this is unfortunately tricky, right? There is no world, unfortunately, where I make all the cell designs that everybody consumes and I can hold all the variables constant. And I can say, you all use the same electrolyte, you all use the same cathode loading, you all use this and that. So what really this story is coming out to is it's hard to really say something is lithium, its equivalent lithium content is better when its cost may be worse. And when you're talking about what makes a battery, cost is always part of the equation. And I think a good representation of this is on the next slide. So we took a 75 kilowatt hour battery pack. We said it would have a 4-volt infrastructure. And we did one where we said all the chemistries get 15 milligrams a centimeter squared of cathode or CAM material, and kept all the electrolyte except, as I said in the earlier slide, solid state and sulfur. All the foils the same. And then in assumption B, I said, okay, I'll do it what everybody think would be the normal way of doing it, which does change the story, which is going to say, all right, I'm going to take a 4 amp cell and I'm going to design every single one of these chemistries to be 4 amp hours. And what does that start to look like in terms of a pack? And on graph A, what you'll see is, well, if lithium sulfur can have 15 milligrams a centimeter squared of CAM material, it needs way less batteries in a 75 kilowatt hour pack, and it costs way cheaper than the majority of other chemistries. So you would just use lithium sulfur in e-base. Right? But if I say, okay, everything's designed to 4 amp hours, lithium sulfur is still cheap, but you'd be buying 3,000 or 30% or 60% more units of cells, which would easily defeat your cost goal, right? So like the reality is the cell design in this whole lithium equivalent content in conversation, it's really the cell design that's the dictator. Costs relatively will remain unchanged per kilowatt hour. And then the other real takeaway is solid state and liquid metal, lithium metal with liquid is always the most expensive, regardless of how you hash this. I didn't do lithium air, and I'll go into this slide in a second, but I didn't do lithium air because that is a fantasy. I have made lithium air batteries. I will tell you right now, I do lithium sulfur and I already consider myself a masochist for doing that. Lithium air is orders of magnitude more painful, and I refuse to do that. There is new technologies that do blend capacitors in lithium ion batteries, but kind of like the comment said, that's really to attenuate energy flow. And then recycling is still in the chat, but like Aubert said, well, that's next talk. We could have like a whole third thing on recycling and our viewpoints on it. So what I kind of did here is I took the watt hours, that is how much watt hours you get per gram of lithium for each of these chemistries, and I did the energy density in the watt hours per liter. I've kept all the same cell designs that you've been thinking of before and all the same ratios. You can kind of see all the dots, which are a representation of the 5 different loadings plus the held constant amp hours for one of the chemistries, which is why you see things get a little bit closer to each other. The slight driver and differences in weight and watt hours per liter are usually a function of the density of the materials used in the cell design. But I think the main conclusions you guys can really draw from this is there's going to be no silver bullet, like regardless. You can't plug in NMC 9.5 as your winner for all chemistries. You can't do that for LZO solid state. You can't do that for lithium sulfur. You can't do that for any of the other cathode materials. The reality of this lithium equivalent content argument is that, volume, weight, and cost are really what drive the chemistry selected. And it's going to be that cost factor. So like equivalent lithium content performance will only likely become a consideration when the #1 factor in what you are doing is cost. And unfortunately, not all markets play that by those rules, or else Ferraris and Lamborghinis and Countach, like every luxury car, Bentleys, Rolls-Royce wouldn't exist, private jets wouldn't exist. Essentially all of these sub-markets that are called luxury goods wouldn't exist if cost was the #1 factor in something, right? Like, you know, we all say like gas prices are important. That's why we buy a Ferrari or a hybrid. But I guarantee if you ask the guy who owns a Ferrari, if he cares about how much he pays at the pump, it doesn't even blip in his radar, because he can own a Ferrari, which means he's got enough money to afford cheap gas.
So,
Jeff,
little,
just a second, for the benefit of everyone, going back to the last slide,
Mhm.
could you clarify, you know, it is well known that the energy density of LFP is lower than NMC or NCA. But if you look at the bottom right graph, LFP is on the far right, indicating higher energy density per watt hour per liter. So perhaps it may help everyone just to clarify how
So-
LFP.
Yeah, it's the y-axis that's actually on the bottom graph, your watt hours per liter and your watt hours per kg. It's the x-axis is basically how many watt hours you get per gram of lithium in a chemistry, right? So there does exist a world where you're getting a very efficient utilization of your lithium to maximize how many watt hours the battery can produce, but it's not really giving you any volumetric energy density. It's just using the lithium really efficiently per unit energy, but it's still a low nominal voltage and it's still a low dense or a lower density material.
Perfect, thanks.
I'm sorry to intervene. Did you use full lithium for your calculation for LFP? Because it's only half of lithium can be used per mole.
Did I use full lithium? The cells were all held at an N/P of 1.1. Graphite was used at 330 milliamp hours per gram as the counter electrode. I did the loading as a dynamic function of the N/P ratio of 1.1. I kept binder content and porosities of all the graphite
What I'm
anodes.
saying, only half of lithium in molecule of LFP could be cycled.
That is not necessarily always the case. Right now, this is assuming full conversion, but it is not always the case that you only use one molecule of lithium or half a molecule of lithium
Half
per
molecule.
crystal. I'd be more than happy for you to show me the data that proves that out, but last time I checked, that's not the case. Or else all of these numbers at full conversion would be off, right? So like, for example, we know that LFP can get above 200 watt hours per kg. CATL has shown it. If your argument is correct, that does not exist.
Well, I think that's at the cell pack level, and with all this, the cell to pack, and then a few other changes to the structure of and then NNP ratio.
The 0.5 is actually for LCO, lithium cobalt oxide, not for LFP. LFP, you can pull an entire lithium out of LFP. You cannot pull an entire lithium out of lithium cobalt oxide because the structure will collapse.
Yep.
so this
Amber,
is
you are
rapidly
pointing out problems I don't want to explain. I built like 50 batteries. Leave me alone.
so this is rapidly heading into kind of equivalent to what Jeff and I did for the battery report last year, which is we did some basic assumptions, built a bunch of different standard batteries with those assumptions and put them up to compare the different chemistries. Anytime you're doing that much stuff with that much different information, there's going to be a lot of little things that either they're wrong or they could be done differently, or there's a better methodology. But for the sake of kind of getting them all in one place with similar assumptions to kind of explore it on a first order basis, which he did in 2 weeks. I think these are pretty good.
Yeah,
I hope you guys appreciate those. And we can try to sort of share how and why we did some of these and kind of publish some of that later once we get a chance to kind of clean it up.
Yeah,
But,
I'd also emphasize,
love the
guys,
discussion.
this kind of goes back to my earlier point, which is cell design is the dictating factor here, right? Like no matter what you do, the cell design is really what dictates what the performance of the cell is. So like, yes, if it's really lithium efficient, that's cool and all, but that only matters when cost is the #1 thing and you're competing with the cell design at that point.
Okay. So again, we're not going to be talking much about the actual, mining or recycling this week. There are many different ways that lithium shows up in nature. There are multiple different mining methods and ways of extracting it out. This is just a transition slide. So basically, where does it come from and where does it go, right? So this is a complicated question. I mean, you look at mining versus recycling versus its use in production, there's a lot of different places and most of them are not the same. And kind of the two caveats to that are right now, the gigafactories being built out in the US, where potentially there will be production of both the materials and of the cells. And right now, basically in China, where basically some of the lithium comes from China, most of the refining comes from China, and most of the battery production comes from China. And so right now, when you look at world reserves, it's basically the lithium triangle in South America, where most of it comes from, or long-term where most of it is. And you're looking at basically right now, the fact that the supply chains for this are global, very spread out, and not optimized. And especially, as both Europe and the US are trying to go into being, gigascale battery producers, you have to overcome this issue. And that's part of the IRA is basically setting up the mining, the refining, and the material making here in the US, because otherwise there is no way to be cost competitive if you're having to ship things that far away and pay the margins on doing all the processing somewhere else.
Yeah, and if you go to the next slide, this kind of just rehashes is Aubert's point, right? Which is like, if you have lithium mined in location A, you're getting it refined in location B, and it's getting used in location C. And that adds tremendous cost to the supply line and the overall end product, right? So like global transportation is a large cost of lithium. But similarly, right, the unfortunate truth is all roads enter and leave China. That is just how things are working right now from a material standpoint. Basically, all the lithium goes to China where it's refined, and then it leaves China to go into its commercial product. And I know there are some suppliers locally. There's Livent, there's Albemarle, there's a few others that produce locally in some certain amount of quantity. But when we're looking at the supply chain, we're looking at essentially where's the most going, right? We're not looking at the 2 to 3% suppliers. We're looking at the 50+% suppliers. And this is kind of the, go back.
Okay.
To Aubert's point, kind of the rationale behind the IRA, right? Which is like for countries to get ahead, regardless of chemistry, regardless of cell design, regardless of anything, they're going to have to create their own domestic supply. And then the unfortunate truth to that is it takes years. It's not quick. It's very slow, which leads into the next slide, which Aubert flashed, which is our demand, which the reality is, when will we have enough lithium? The answer is not soon enough. So this is from Bloomberg NEF, one of their articles. Essentially, they're showing 2015 to 2030 with the CAGR of demand through different sectors of like e-bus, EVs, stationary storage, consumer electronics, and all of that stuff. And even in the article themselves, which I find interesting, we have linked here, is they say that 48% of the capacity that we are basing all this demand curve on is being produced at non-tier 1 producers. What that basically translates is that almost half of our predicted supply doesn't actually exist. And it is in the hands of small startups and new companies trying to break into the space to produce at technical grade for batteries. It's kind of a scary thought.
So, and, all of these numbers are highly contested, debated. There's a lot of different opinions. You see a lot of the investor class of predictions going, business as normal, everything's fine, keep putting your money in, let things continue as they are. And you see people like Benchmark Minerals and other people going, no, there's a real problem that needs to be addressed right now if this is going to work out medium term, let alone long term. And a lot of people kind of in between. And so it's really interesting to see kind of where people predict the shortages are going to be, where they predict the forecasts of production are going to be. And really right now, a lot of this is, again, like we said earlier, more battery factories for EVs equals more demand equals more people scrambling to get their supply lines in place and their long-term contracts signed, which pushes up pricing, right? And then the equivalent is you see a lot of people canceling or delaying their gigafactories and their production, which then means especially if they already have their supply contracts in place, they're going to have to basically offload them at lower than that to get out of them or pay big fees to escape them. And that's going to do the reverse. And so my personal kind of opinion on why, the pricing did this and then briefly dropped is we've had an enormous number of companies basically cancel or delay their gigascale batteries in the last half a year. And I think that's a big piece of it. And basically, like any market that's volatile, the last couple percent is what dictates the pricing. And basically, the more changes that happen in what people are predicting they're going to be using versus predicting they're going to supply versus actually supplying, the more that's going to fluctuate wildly.
Yeah, and I think this is a great plug for what we'll be talking about next time, which is actually we'll be going over the timeline to build a lithium mining facility that exports materials. We'll have that whole. We're not going to Gantt chart it on like, we hired person A, they went to person B. We're going to Gantt chart it on estimates of how long it takes to get, environmental certification clearances and everything else. But like, we'll have that whole timeline. And what you'll be surprised at is if they aren't building today, they probably aren't going to make it.
One more thing to just mention is, and this is a industry-wide problem for lithium-ion, lithium metal, is that basically the pricing ends up getting pegged to the highest paying chemistry that has the most buying power, the highest margin, and the biggest demand. And so if you have low performing stuff that takes the same inputs as a higher performing, higher valuation product, you get absolutely screwed because you're paying the same input prices and you're not getting the same output income coming in when you sell them. And so that's one of the other really big problems, and like the difference between the level that you're producing at and also the quality of your perceived product. And that's right now, that's a really big problem. Okay. So lithium production, and again, just a little bit more on this, but basically, capacity has been going up. People are improving it as much as possible. You can see where it's being done on the right. And it's, again, like Jeff alluded to earlier, very specific places, right, that are doing most of the production. And right now it's really Australia, Chile, and China. And again, it's not going fast enough. Anything else you want to say on this one, Jeff?
No, we're good.
Okay. Oh, okay. So that is actually it for the first presentation. Happy to do more questions and comments right now. The next one, again, is going to be mining, refining, and recycling. And we're going to go into the different steps, the processes, some of the different chemistry for basically getting to, the lithium carbonate to lithium hydroxide, and some of the other things like that. Some of the newer announcements on different process technology people are doing for the mining and recycling, which is really interesting. Enormous amount of development there right now. Hopefully one of those ends up being much faster and cheaper and can help sort of solve this problem, which would be wonderful and let us make, more better, cheaper batteries, but we'll see. And I think that was almost perfectly timed because we're going to get kicked out any second now. So thank you all for attending this. Jeff and I will both come back after this to just talk more and answer questions, because for us, that's the fun part, is talking to you guys and discussing. But have a great rest of the day if you're not coming back, and we'll see you again soon.